Can I have your attention, please, for a minute? We're about ready to start. If you could start working your way into the theater. And the good seats are going fast. I think there are still some in row 36. I recommend you move on into the theater pretty quickly. Thank you. So George just stepped out to call Kurt one more time. So he's coming back in right now. And
I get the door? I think this is working. It is. I think the ambassador already welcomed you to the Baker Institute, but welcome to our international conference facility. This is where we have a lot of our meetings. We have 2 translation booths on either side, so a lot of our international meetings are held here. But we're very pleased to have you here at the Baker Institute, and I think you'll find today to be a very interesting one. And I'll introduce Kurt Sharman, who's the manager of the International Space Station program. He's going to be the chair for the session this morning. Let me turn it over to Kurt.
Good morning. It's a pleasure to be here, especially with such a distinguished group. It's really great to see all of you here. Hopefully I have a chance to visit a little bit. It's been a busy time on the International Space Station and human space flight. And it's really a day doesn't go by where I don't think that what's going on today with our humans living and working in space wasn't the result of all of you and the work that you've done. Here a week ago, we were conducting a spacewalk in a series of spacewalks to replace batteries, which to the outside world sounds like a simple task, but I bet to you, you probably have a much better appreciation of what it's like taking a refrigerator-sized battery, slinging it across the truss 230 miles above the Earth, traveling 17,500 miles an hour. It worked magnificently, by the way. The EVAs were accomplished perfectly. But the day last week when we were having that EVA was also the day, in fact, we just started the spacewalk and learned that Alexei Leonov had passed away. And it wasn't missed by me, it wasn't missed by our team, that here we are today doing this task, and it was really, really on the shoulders of Alexei and many, many others in that line who've allowed us to do what we're doing today. I stand here today in front of you, and we're preparing to do a spacewalk tomorrow. We'll be doing a spacewalk tomorrow, which has some significance. It has significance because tomorrow, in the spacewalk last week, we put all the batteries in there, and they worked great, except for a box that was right next to a battery, and it didn't work so great. And unfortunately, the battery box right next to it was a battery charge discharge unit. So unfortunately, we have a nice healthy battery that can neither be charged nor discharged. So we'll be doing a spacewalk to go replace that box tomorrow. As is the case, we select crew members to do a spacewalk based on a lot of factors. The tasks being done, of course, all our crew members are certified to do these task-specific things. And what else is going on and gaining experience. And so tomorrow we'll have Christina Cook and Jessica Meir performing a spacewalk, which I'm told is the first time we've ever had 2 women outside performing a spacewalk together. So it's great from that perspective, but I from my perspective, they're accomplished crew members, and I know they'll be able to do that spacewalk perfectly. And there they are taking pictures of me. So very excited about that. Yesterday I had the pleasure of being in Louisville. Help me out, Jim. Louisville, is that how you pronounce it? Louisville, Colorado? And Louisville's right next to Boulder, right north, I guess, northwest of Denver. Beautiful place. And we were looking at the Dream Chaser structural element was delivered to Colorado. It was manufactured actually in Fort Worth, Texas, and put on a very innocuous truck wrapped in nice plastic and driven up there. But that vehicle hopefully will be flying to the International Space Station, a winged vehicle carrying cargo, very, very soon. And I know that Sierra Nevada at least has dreams of putting humans in there at some point in time. So I think we'll put live animals in there first. We'll see how that goes. But then we'll go on to humans. Anyway, I know you guys didn't come here to listen to me. You came here to listen to a very distinguished group, and it's an honor for me to be here today and to be associated with this distinguished group. So our first presenter is Dr. George Nelson. George works with the International Space Station in technology development. Really, George does a lot of everything. And in fact, George is responsible for organizing a lot of the session that you'll see today. So George has many skills. He helps us not only in performing the technology development that we're doing on International Space Station, prioritizing that technology development, but also in our commercialization activities on the International Space Station. So with that, let me hand it over to Dr. George Nelson.
Thanks. It's nice to be here. The last time I was here, I got to listen to General Engel talk about X-15 flying and to see the enthusiasm in the room that day. I'll be doing pretty well if I can keep you guys as interested as that crowd was that day. So, I think I'm going to end up driving this, and let me know anyone else if I'm not the one who's supposed to do it. I'm going to give you a quick overview of the premise of what we're trying to use ISS for in our enabling of exploration, and then give you some specific examples before the rest of the panel today ends up talking some down and in details about some important ones that we're doing. So, historically, the agency has used one program to feed another through reducing risk and improving technologies during that first program. So, Mercury enabled Gemini, enabled Apollo. So we're using the ISS in a very similar way wherever that next destination program, all of them end up sending us. So in case you were wondering whether I was an ISS person, a JSC person, or a headquarters person, the first part of this presentation will solidify the fact that I'm a JSC person. Lots of words on these charts. And then when we get into some specific examples, you'll see some maybe more entertaining things there. But so we know that the long duration missions are going to require capabilities that we didn't have full confidence in when we started doing a lot of these technology demonstrations on ISS about 9-10 years ago. Including just the vehicle itself. But we recognize that buying down that risk in the proper environment has great benefits. So if you're trying to get to a particular TRL or a technology readiness level for these technologies, doing it on ISS allows you to get there without putting your vehicle at risk or crew at risk. You already have a full bus there. You have a crew that is relying upon proven systems in low Earth orbit, but it's a relevant enough environment for a really broad set of exploration technologies that you can have confidence having flown it on ISS before you fly it cislunar or beyond. It's been pretty important that we've had our international partners involved with this, whether it is sharing cost, whether it is looking at dissimilar redundancy capabilities that we're trying to prove out, or whether it's, hey, you take this one and we'll take that one, and divvying up the cost. Because the cost of trying to test the next program while flying the current one is not an insignificant budgetary challenge. So whether you're an engineer who cares or whether you're an OMB person, there's a certain threshold before you maybe want to trust. I think we have a different relationship with risk than we had maybe when we first started flying people in space. And so when you look at the people who are cutting the checks and even the people who are running the programs, you look at what technology readiness level you're really looking at for putting on that next spacecraft. And so there's a general consensus that you want at least a 6 or a 7 of technology readiness before you implement that. And ISS is capable of getting you there. So we ended up identifying particular areas that we knew ISS could help us with. And so it was about 9 years ago, we and the partners together said, all right, how are we going to best use ISS for exploration? And we put together certain teams to figure out where we were going to focus, what we were going to do. We've had multiple iterations on how we managed to focus on these different areas, but these are the ones that we knew we could get a significant return on our efforts in low Earth orbit. Low Earth orbit's not the same as heading out deeper into the solar system in every respect, but in many respects, we could do these areas quite well. So we've already been pretty successful in some areas. I don't think we're there, but the goal about a decade ago was for us to have a full understanding. What do we need? What do we need? So that then we had to make some assumptions about where we might be going, and then tried to organize this as something you could measure, a performance to plan. How are we doing on checking off this box, off this box? It was really a consensus that the longest pole, the thing we were most concerned about was the broad array of ecosystems that we knew we needed to prove out. And so Laura Shaw is here, and she's going to speak the specific efforts that we're making on ISS to buy those risks down. We've had some success in that area and others so far. And let me give you a few examples. So the rollout solar array was, this will be on a loop, but the rollout solar array was one that we, the government, the United States government, had invested in through a small business area. We knew we wanted some lighter weight, next generation photovoltaics for whatever the next mission was going to be. Within our agency, we had people approach us with different designs, not even a determined design, but they said, hey, we'd love to give you a solar array. At the time, we couldn't figure out how we would be comfortable deploying an experimental structure on a vehicle that occasionally needs to perform a debris avoidance maneuver, or just simply we would prefer not to have something broken hanging off the end of the vehicle and risking the vehicle itself. So when the Air Force Research Lab came to us and said, we really want to test this particular design, the initial answer was, well, we've looked at trying to test solar arrays on ISS, and we couldn't manage to get ourselves comfortable with it. But we kind of doubled down on looking how might we be able to do this. And so our teams in integration, we have some former robo people, we have plenty of power people, kind of looked at how will we get to the objectives. What are the objectives? We want to be able to show that this particular design was going to be deployable and can it even be retracted. So we figured out a way that we were comfortable demonstrating this. We did it off the arm. We pointed it retrograde so that we knew if there was an issue, we could get rid of it. And so this was a successful deployment, and you're going to hear more about this from Eugene Schwanbeck at the end of today's session, because this helped inform not only the power and propulsion element for Gateway, but also the replacement arrays that we're going to install on ISS. So the question that I'll often ask people when they come and say, hey, I have something that I really want to fly on ISS is, could you tell us not just your objectives, but how those objectives are met in the specific microgravity environment that ISS provides. And so when you look at liquids and propellants, it's evident, especially when you have a see-through canister, why you might want to do some of these tests. So whether it's trying to figure out how much fuel you have left in a tank, or whether it's just a fundamental understanding of what these fluids are doing, it's a benefit to do this. So this is the slosh experiment. This is one that kind of straddles applied physics and engineering. We have a lot of that kind of sits on the fence, and then we try and make sure that we utilize that information the best we can to make future decisions on programs. We've performed these tests with attaching it to a facility on orbit called Spheres that can autonomously fly around, or we've just imparted the loads specifically and then done plenty of analysis of these images on the ground to figure out what we're doing. one that was a kind of a quick return. So we do have some, even before Artemis was announced, we've been preparing for a long time for whatever that next mission is. And Orion has been in production for a while now. And while they had a primary navigation system that they felt they had some confidence in, when they wanted to see what their redundant system might look at, they said, well, we believe that the crew might be able to help with this, or we could have our own redundant cameras outside and verify our navigation optically. So we use the ISS crew in order to look at the limiter of the moon while we were orbiting around the Earth, to be able to verify for Orion that the redundant system that they were planning on employing on Orion was something that they could really rely upon should the primary system ever have a problem. So this was one that we managed to get done almost in crew spare time. We ended up scheduling it a few times, but also was able to take care of things, over a Christmas break when a lot of PIs on the ground are not available to do work. This was something that was able to get done a couple times, a couple different iterations, and proved successful for that project, Orion. This next one is one of the more interesting ones, I think, that we've flown so far on ISS. So NICER Sextant is a combination of an astrophysics experiment and an engineering test bed. So this is looking at X-rays, and I won't go too far because it's not the topic today into what it's discovering in the universe, but what it's proving for us is that we can use X-ray sources, these pulsars throughout the universe, as kind of a galactic GPS. So you think about the constellation that's above our heads right now, where we're walking around the Earth. You don't have that necessarily when you get further out away from the Earth. So using what nature has provided us, these relatively static and reliable X-ray sources, was something that had been postulated as possible. And so we've done multiple tests in order to do that, and I don't want to misstate the accuracy of it. So we got within, and I don't see it in my notes right here, but I know we were able to get, it was one order of magnitude better than what they thought the minimum required accuracy was in order to say that this was a viable solution for us. So this was just largely a science instrument funded by the Science Mission Directorate mostly, and built by a big group of people, Keith Gendreau at Goddard. Yes, sir.
George, did you say the sensor is X-ray or is it radio?
So it's sensing X-rays. Yeah, so it's X-ray nav. That's sped up about 100 times, so don't think that is gyrating up there quite that dangerously. And every other scientist would be wondering what kind of...
The Voyager spacecraft used pulsars for the spacecraft that's out there now to show the origin from whence it came, so that this concept is not entirely new.
No, I think it had been batted around for quite a while, and being able to have a vehicle that can already verify its location with our existing GPS and comparing it to this X-ray navigation, I hesitate to say it, but I think it was within 35 feet, I think, is what they managed to do, which is pretty good at the speeds that you're talking about.
But they use radio pulsars. These are using X-ray pulsars.
Oh, with the Voyager one?
No. This is X-ray pulsars. Voyager was radio.
Radio.
Okay, that's how I understood it too. Thank you. Okay. All right, kind of similar to that slosh experiment that we mentioned, the zero boil-off tank. So there was plenty of discussion within the agency that we needed to have a very large-scale demonstration of fuel boil-off to try and figure out how to mitigate that. Whether it was going to be something stored at a fuel depot and needed to be there a long time, or whether it was just a long duration mission that you really didn't want to lose that much fuel and you had to figure it out. So this is an investigation that is on the fundamental physics side, but they recognized the applied physics side of it quite easily and managed to talk to the people on the Space Technology Mission Directorate side and Advanced Exploration side to say, yeah, we all want to sponsor this together. And so there's probably going to be further iterations of the zero boil-off tank, but this is investigating the thermal properties and how they restrict our ability to keep cryogenic fuel on orbit for long periods of time. So Sapphire was one that came to us. This is an investigation from Advanced Exploration Systems, which is a branch of the Human Exploration Operations Mission Director at headquarters. When they first brought this to me, they said we have lots of data on very small scale fires. You know, we have the FIR and the SIR on orbit, so we have this combustion rack where we do small scale fires, but we had very little, no data on larger scale fires. Some people who are on MIR might say different, but we didn't have the real straight data for this. So when this came to me, they said, well, how are we going to do this? And so we looked at some of the vehicles that we were already burning up, the Cygnus from Orbital at the time, now Northrop. And so I was really excited because I had in my mind this Wrath of Khan style fireball out in space that was going to be happening before we deorbited. But it was a much more controlled thing. There's a somewhat large box that we put inside of the Cygnus. There's video here that gets fed down to the ground for us to do the analysis. This particular one is Sapphire 1, and so that launched back in 2016. And understanding how this all, the green flashing is to show is to get some contrast for some smoke. You know, without convection, things do a little differently. But the easiest explanation for this is there's somewhat long, elongated strips of material that you end up burning from the right-hand side to the left, and they end up getting their data from that and informing other designs for fire mitigation, for prevention of the same problems. Phase change material, heat exchanger. This was an investigation that came about in a couple different ways. We ended up having multiple directorates across the agency kind of come together with this. When we first started using ISS in earnest after assembly completed, we had a little bit of a challenge letting everybody know that it was theirs to use. We didn't have a research budget specifically allocated to fund all of these investigations. It was up to the individual directorates across the agency to take advantage of this vehicle. And so this was a success because we kind of felt like movie producers putting everything together, and I would always lie to Kirk and Suff last about who was on board. And so we got to the point where STMD was giving some money and AES was giving some money, and then ISS would say, okay, we'll pay for some young engineers to put this all together for you if you pay for the commercial aspect of it that's bringing in, you know, this other piece of hardware. So this was one of the first that we managed to get multiple people sponsoring and paying for an effort on ISS. It ended up paying off the same way that the ISS partnership does, right? You can't, not one person is going to pull out even if there's a budget concern because there's 3 other people trusting them to stay in it. So that's what this was. And the effort for this was trying to specifically look at the low lunar orbit applications of thermal control when you're on the backside of the moon. So when you're on the dark side, apparently there were some problems even on Apollo with, you know, if you grew up north like I did in Maine, you wonder, if you didn't grow up in Maine, you might wonder how, when it's minus 20 degrees, your car's overheating, but it's because, you know, your antifreeze froze anyway. So it's this sort of thing. It's taking advantage of the fact that you can store thermal energy in a solid and waiting. So there was 2 applications. There was a water and a wax. This was specifically for Orion for that case, and we were able to prove out something for Orion again, and they're going to utilize this going forward. It doesn't have to be hardware all the time. So we've also looked at disruption-tolerant networking. And I'm running out of time a little bit, so I will skip through this. But understand that, you know, this helps with just verifying, you know, comm, whether it be data that helps you navigate or anything else that helps your spacecraft get where it's going. This is something that works on the ground, but we've been able to employ it on board ISS for payloads and other options, and it helps instill a confidence in whatever next program is going to use the same premise. Just for our own sake, we've employed RFID on board, but we know that when you're halfway to wherever we're going. You don't want to have to spend most of your time looking for that wrench or that piece of scientific equipment when you're doing it. So we looked at this. It's not just deploying RFID tags like we have on all our cars or our passports. This includes the algorithm that helps you determine where the most likely location is for something, because these don't necessarily work perfectly when you have metal shell, racks, and other things that are in your way. We also look at radiation. Now, the radiation environment is not the same in low Earth orbit as it is where we're likely going to be going next, but we've done a ton of sensing. Now, the criticism I always have with everybody is we sense the crap out of this stuff, but it really just gives you the capability to say you're smoked. So we still would like to hope that we can get to some mitigation steps downstream, and whether that's on ISS or elsewhere, we'll see. This is just summing up that we've done a lot of work across the agency, and I think I got that point across a couple times. And so it hasn't just been ISS, but we've been effectively utilized by the entire agency and even some people without in getting our our technologies demonstrated appropriately on ISS. So I'm going to sit down, and we'll hopefully have time for some questions from everybody after. JD, is that your preference?
Your preference.
Okay. I'll take a couple. Okay. All right.
All right, thanks, George. The really cool thing about what you're seeing there, in some cases, taking a tool that we had and utilizing them in different ways. So, for instance, that NICER that George was talking about. We actually used it for an X-ray comm experiment as well. So it's really cool how people can figure out how to use the equipment that we have on orbit for many different purposes. Let's see. Next speaker, I believe, is, okay. Jim Broyan, Advanced Exploration Systems Logistics Reduction Project Manager. That's a mouthful. So he does logistics for autonomous tracking and trash management, long wear clothing, and Orion toilet. That doesn't sound like what you would want to do around here, but you all know in space that's a big deal. Logistics is a huge deal for things in low Earth orbit, and will be even more critical as we go forward. So with that, I'll hand it over to Jim. Thank you very much.
Great. All right. Thanks. I appreciate the opportunity to come talk to you today. Everyone in this room is probably familiar, maybe more than you want to, with one of these systems on here. The exploration toilet we're developing, we worked with George to put out an initial call for this. It was originally going to be just a quick demonstration on ISS. But then, as he mentioned, how do we use all the NASA resources? We asked Orion to pay for some AES program and an ISS program to pay. And so it went from being just a quick tech demo to we're going to support ISS expanded crew operations continuously after the tech demo. And we're going to build the unit for the first Orion manned spacecraft for EM2. And so it evolved pretty significantly. POTI has many names, WCS on the shuttle, the ASE on the Mir, the Soyuz, and the Russian segment, and the WHC on the US segment. When we started this project, one of the things, everyone who's done spaceflight, OPNOM's important, and they were going to have a meeting on what we were going to call it. And it's like, this is going to be the best meeting of the month. And we go there, and once in a lifetime opportunity, and the push to call things what they're really known as, toilet system. So it was a little bit, makes sense. It was a little bit not what we were going for. You collect urine, feces, but menses, emesis, things we don't often talk about. You're very familiar, unsuccessful operation can soil the crew, the cabin surfaces, create escapes of fecal and urine material, creates noxious odors during collection, as well as the stored material. And then particularly on the urine side, we either vent the urine to reduce vehicle mass, and we've had trouble on the space shuttle with precipitates clogging. We fouled a separator. Fortunately, the shuttle had redundant separators. And on the ISS, we process urine, and so how we pre-treat that, sometimes store it, is really important, requires a different solution. And then if you don't do treatment properly, you can create ammonia gas, which is problematic for particularly some of our exploration systems. It can contaminate the CO2 removal systems. Why is it difficult? I probably don't have to explain that to people here, but everyone's body is different. The men, women, people use the potty differently. We have surface tension dominating. Your body's covered with a lot of hair in some places, but tiny hairs everywhere. And so stuff wants to stick to you more than it wants to stick to our hardware. And so we use airflow to pull stuff off, but you can use too much airflow is problematic as well. It creates a lot of turbulence. Vehicles are usually more focused on things that can hurt you first. The rocket, making sure you have oxygen, making sure you have pressure control, water. And so potty systems often don't get the type of attention they deserve, at least in our opinion. You have volume constraints. You have to fit them in the vehicles, particularly as vehicles get smaller. And it's really difficult to validate the hardware on orbit. You can't really make much in the way of subscale models because you're talking about, human anatomy. How do you, urine is a little easier to replicate. Feces, how do you replicate its separation from the body? And there's been some zero-G gravity flights we've done with partial success. When we started looking at this back in the 2006, 2007 timeframe, we surveyed the previous systems. All systems have used airflow since Skylab. There's 6, depending on how you count the various configurations, 6 US and 3 Russian systems. They've all worked well for some crew, but not all crew. They haven't had a system that's worked well for the wide variety of ways people use them. I'll say most of our systems have been designed by males, engineers, and so the systems aren't real suitable. They have a lot more escapes for our female crew members, which we're looking to really correct or address, primarily in the areas of simultaneous urination and defecation. So you have odor controls. Our systems, this does not have the ISS on here just from the time frame. We put this chart together. We were surveying. We had not yet built the WHC with our Russian counterparts. And we have good experience with the Russian ASE toilets. Requires some frequent component change out, but that makes it very serviceable. So there's things you have to trade. A little more, some pictures here with some titles. I'll start up with a quote from Apollo 10. Sort of sums up the Apollo bag, which almost everyone who's flown on a U.S. spacecraft has seen as the backup piece of equipment. And so you had Skylab, the first potty with airflow, the Russian ASE, the U.S. Space Shuttle, which had a fixed tank, dual rotary urine separators. The EDO WCS flew 4 times. Some of you, a small subset, have experienced it. It had a fecal canister you could change out, which was one of the main drawbacks when they were looking for extending the shuttle life, was the fecal can was sized for the initial mission and it couldn't be changed out. And so there was a lot of work on how you could have that rotary vein compactor in there to increase the capacity, and you had to put your toilet paper in a different container so there'd be more room. So things we tried to avoid. Very popular for crew photo ops, YouTube videos. It's an international phenomena. All our crew members take photographs of it because the public's very interested in it. It's a common question. It's popular. Big Bang, probably everyone's seen that. Some crew members have been on Big Bang. The Wallowitz zero gravity waste disposal system fails and requires an emergency EVA and to get away from it in one episode. It's been on a small piece of Star Trek, Apollo 13. If you watch closely, Tom Hanks is using it back in the corner. The orange bag floats past the screen. Martian movie, throwing potatoes in it, that might be a little bit of a stretch, but I like the inventiveness of it. Packing for Mars was a whole chapter on separation anxiety. But internally, less so. You think about it. You don't go home and talk about how did it go for you this morning with your partner. And we don't do that here. We talk about how did the hardware work? What was your experience? And so we really worked hard to communicate both between the engineers and the crew, as well as between crew members. Originally when we started, crew debriefs were basically gender specific. You generally had female people debriefing the female crew and male crews, or male people debriefing the male crew members. And so if most of our engineers designing potties are men, you can see the immediate problem. And so we worked, and we now have very open crew debriefs that are mixed gender. We had a whole wide range of sessions. We approached the crew office early on saying we really wanted to address some of the challenges our female crew members were having. We had some initial, all-female sessions, and then we had design thinking where we picked on different aspects. We have 2 or 3 crew members to get some discussion. It was very interesting when someone would say, "Oh, I didn't realize that was a problem for you," or "Oh, I never thought of that technique." We did multiple seat evaluations. We did funnel evaluations. We flew 3 funnels up on, I guess we call it NG9. And got feedback that we're modifying. So when we fly the real, or the UWMS, we will fly modified funnels to try to make things better. And so as we go forward, one of the things we try to push on is not to make an optimal toilet for someone or a particular way of using it, but making a toilet that is acceptable to the widest range of ways of using it. Some people hover, some people get full contact, some people contact on the back, some people contact on the front, some people have to do on the existing toilets, a pretty significant pelvic tilt to be able to try to get simultaneous urination and defecation. Potties, complicated. Space station wasn't designed for an extra potty in node 3, so we had to figure out how to shoehorn that in. This picture, this does work, okay. Down here shows you this is where the ASE, the WHC, is in this rack volume back here, this operational volume, and currently the ASE stall, WHC stall is here. And there's this mid-bay, this partial rack here. That's all the volume that was available when they looked at the whole space station. And so we put both in there, and you can see it's really packed in here, and I'll talk a little bit more about it later. And Laura will talk about some of the challenges of integrating exploration, but this is the dual stall here, and then there's the exercise treadmill right here. But it connects to lots of things you can see over here. But let me just jump ahead. There's a picture of it. We flew the stall on, it's not NGXX. I'd like to say it's NG10 that I just double spaced, but anyway, mistake on my part. We flew the stall up, it got test fit. One unique problem was the WHC rack floats. It's not rigidly attached. The mid-bay does not, and our structure goes around both pieces. And so we had to make the stall rigid enough to take the reboost loads with basically supporting a floating rack on one end. We also wanted it to be very maintainable because it's on top of a bunch of stuff, the urine processing, some oxygen equipment, brine drying experiment that's going to go. So it has to come all apart, and it's got to fit in cargo bags because we can't launch racks easily anymore. But so that is ready. It's for when we launch the toilet system that'll get reinstalled. It's been temporarily uninstalled. The left side. Thank you, Laura. So we will fly on a SpaceX 20 currently for ISS, but we'll actually deliver the ISS unit first by a month, and it'll fly, because it has a long integration time period. Oh, sorry, Orion, thank you. We'll fly the Orion unit, or deliver it early, because it has a long integration period before it can, other things have to come. Let's just see. Here's a picture of the potty, both, it's a compact, button. It's a common structural core. It sits out sort of in the aisleway, and everything is mounted to it as a dual fan separator rather than having we have 2 fans, one for urine, one for fecal collection, with separate airflows, so that if you're using one or the other or both, you get the same airflow. That prevents sort of the equivalent of you're taking a shower and someone uses the water and you get scalded. It also, rather than package basically a single cylinder, the dual fan separator, rather than we have a cylinder for a separator, a cylinder for a fan, a cylinder for a second fan. It also has a concentric hollow core odor bacteria filter rather than another cylinder that goes around sort of the opening of where the toilet seat is. And that's all because the Orion vehicle is so small to make the potty as small as possible. Not as maintainable as our current WHC toilet system, or require a few more pieces, but that's sort of the trade-off. Do you want it to be really compact, or do you want it to be very maintainable? Some features to point out here: it does have a seat that's rather pronounced. You might ask, why so high? And one of the reasons is to give a better angle for the urine funnel for female crew to improve their collection, hygienic collection, because it's not enough to get the urethra in the opening of the funnel. You want to sort of get it along the axis so you have less ricocheting. That's a real problem on the current toilets. We do have the capability to change different toilet seats out. So as we get crew feedback, we're going to fly 2 initially. We can make easy changes. We can change the funnels out. We'll be using the same alternate US pretreatment chemicals, but that container's now out in the cabin, not protected by the rack, so that needed separate protection from kick loads. We had to worry about, there will be escapes. How do we protect vents and fans going into the logistics module behind us? Let's see. So we're going to fly to ISS. We're going to do roughly 100-day continuous operations as part of the tech demo. And then we'll transition to long-term use for ISS expanded crew size. We're going to evaluate at least 2 seats. We've already evaluated 3 funnels, and we're going to fly 2 modified funnels based on that experience, and we'll likely fly some additional ones. Challenge with funnels is we're trying to come up with a common design rather than a separate male and female design. And so part of the crew evals we've had is feedback. We'll get people say, I prefer this one, but by informing them of some of the challenges of both gender, they say, I can make this one work, rather than the crew having to change funnels and store that used funnel somewhere, which we did on the shuttle. We'll do some photo documentation, acoustic surveys. We want to be able to operate the separators continuously. It provides us some, in theory, you could use it as a shop vac at some point in the future for some of our smaller vehicles. Our current separators only can run for a certain period of time. You have to worry about some thermal issues. And then we'll operate for a minimum of 3 years. And then we do have some planned work to how to reduce the mass and volume of the fecal canisters to support longer-term exploration missions. And I think that's all I have. Thank you.
All right, thank you, Jim. The interesting thing about toilets, lots of interesting things about toilets, but not only the technical challenges that you heard about, they're a big part of our conserving water in particular, conserving resources, you could say, for a long duration space flight. But they also go into international politics. So today on ISS, we have 2 primary toilets. We have the third that we were just hearing about, but to buy the parts for those, we buy all the parts, or the majority of the parts, from Russia. So we actually today we have a law that says starting after December 2020, we can't buy parts from Russia. So we actually need an act of Congress sometime between now and December of 2020 in order to make that toilet work. So I think we'll get there. I'm not worried about it, but it's interesting that toilets are involved in international politics and trade as well. So lots of facets to that.
Couldn't 3D print them?
Well, some of the things are like containers with urine pre-treat. So there's acid and containers, and the kinds of 3D printing that we have on orbit today, anyway, are limited in the types of materials they have. So perhaps eventually, but not currently. We couldn't. Let's see. Our next speaker, Reinhold Ewald, you guys know. He currently is a professor in physics, I guess, at the University of Stuttgart. And he's, as I was reading through the material Apparently he's bilingual because all his education is bachelor's, master's, PhD, all was in physics, and he's going to talk about a bioreactor. So he can speak physics and biology. So anyway, it's my pleasure to introduce Reinhold. Thank you very much.
So, if I had known in advance, I would have proposed to swap the talks because I'm talking about nutrition as well, and you are talking on the contrary. So we back up now, go up. Actually, I'm very honored to present this experiment that we lately flew on the International Space Station, and I tried to get all the inputs now done that this group of people that prepared it in the Stuttgart University under the lead of Ernst Messerschmidt has done for 5 years or so. Finally we made it into space, and this is going to show that exploration, going out, inventing new things is in the mind of the people, of the young professionals that do it. We can calculate the euro or dollar per investment, but the mindset is of a greater value even. These people go out now and have flown an ISX experiment, and that sets their pace for the future. So I want to introduce the algae-based photobioreactor experiment at the ISS and tell you about our experiences now that we have flown a first such experiment. Why would we use a hybrid life support system comprising algae, comprising biological components? Well, you can't take it all with you if you're heading for the moon, if you're going farther out to Mars. Logistics dictate that you recycle as much as possible, but that you have also regenerative components, especially in your life support system. And this is the idea of reducing the resupply mass, of minimizing the system mass that you take with you. There are break-even points, as you can see. You can take it all with direct supply, then you have a steep incline if mission duration increases, and you will have to take a lot of clothing and a lot of oxygen canisters and stuff. You can do physicochemical. This is the dotted line. This is what we are doing right now. We try to recycle by using physicochemical regenerative elements, but we are not producing new things from where we can gain oxygen and stuff. There you need to have a hybrid system. And on the long run, this hybrid system is more effective, even if you have a larger launch mass, to produce your necessary consumables while you go to Mars, for example. And one of the systems that you can investigate is using biological components to recover oxygen, just like the plants do on Earth, by taking the CO2 out of the atmosphere and producing also nutrition on site. You can harvest biological systems, and you close the loops by not throwing away what we give up in the toilet, but reintroducing it on the other end in order to feed biological stuff to the plants. And why do we use algae? Well, algae do exactly this job. They take away CO2. They do it in a large scale on planet Earth, on spaceship Earth, more even so than the rainforests and things combined. So this is a very efficient system that has developed over millions of years. They have a high biomass productivity, and if you compare it to, for example, experiments flown with tomato reached something like 30% of the dry mass as nutrition. Algae are 100% of nutritional value in your harvest, and this makes them a good candidate. And they use nothing but light. So if you put them under light, they start reproducing, they start producing all this with a production rate that is 5 to 10 times more efficient than higher plants. If you want to grow a higher plant, some of you have done that, salad or stuff, you know what you cope with, you get fungi, you get all sorts of difficulties. Algae are very efficient in reproduction despite more or less uncomfortable environment. And the rate of energy you get from algae is much higher than from the salad leaves and stuff. So all of is pointing to using a very simple system like algae in a regenerative process. The group in the University of Stuttgart has then started to select the right species of algae. There are a couple of candidates like spirulina or chlorella. We decided finally on chlorella vulgaris, and this is the result of a long-term experiment, almost over a year of algae production enclosed, no new feeding of algae, just the reproduction under the right conditions produced this constant level of biomass in the algae reactor. You see such a flat panel airlift reactor over here. It works on the ground, but it doesn't work in space because it relies on gases floating through the reactor that you can't count on in space. So you need to go into space and come up with something that would work in space. And we teamed with an experiment that was lately introduced and a life support system equipment that was lately introduced in the space station, the life support rack. And Alex has a good memory of that, as you can see. He was the one to commission that rack last fall on board of the International Space Station. And with that rack, you are able to close the loop. You get the CO2-rich air. You remove the CO2, feed it to the photobioreactor. That's where we come in. Or do a Sabatier reaction. You produce water that you can electrolyze, again gain O2, all through the biological process. So we are about to close the cycle, the big biosphere cycle that we have on Earth, and reproduce it on board of the International Space Station. For the photobioreactor experiment itself, the goals were to prove functionality and feasibility of a hybrid system. Would the algae grow just as they have grown in our lab? Would they behave differently? The short and long-term performance of this photosynthetic conversion using concentrated CO2 from the LSR, from the life support rack, and convert it into biomass, and finally also have oxygen ready for the crew to breathe. And the stability, would they behave the same as on the ground in a real environment? Now we have micro-G, we have enhanced radiation. Would the algae tolerate that? Our launch was with SpaceX 17 on 4th of May 2019, so very recently. And these are the components of the photobioreactor. First, there's this link between the life support rack, giving off concentrated CO2 into our system. We have the supplies in a mid-deck locker box, including a reserved bottle of CO2 that we use in case we are not connected to the rack. And we have the photobioreactor itself. This is the experiment cell, let's say. It's shielded from the cabin air, and in there you see a pump pumping the algae through photobioreactor A and B, 2 units. And they are enlightened, they are radiated by 2 LED panels each that have blue and red LEDs to optimize the conditions for the algae. You need to move them. You need to move them out of the light into the light to reproduce their natural cycle where they are best feeling and have best productivity. And we didn't show the valves here, but for sure we can take samples and we can feed the oxygen into the cabin if need be. This is the heart of this photobioreactor. This is the panel where the algae go through, and it's enclosed with a membrane that allows CO2 in, allows O2 out, but does not allow the water out. That is the micro-G solution for that flat panel reactor that I showed earlier. and the amount of fluid in those two systems is about 6 liters. And you see here the LED panels with the different lights. It's a blue and a red component, and that matches the absorption peaks of the algae. Interesting enough, with the blue light, we enforce cell growth, so they are feeling well. The individual cell grows, and with the right light, we enforce proliferation. So we get the newest generation done, and we fought long for the right mixture of light and the periods that we expose the algae, and finally think we have come to a very good solution. That's a close-up. Here are the LED panels, and here's the algae fluid moving in the spirals of the photobioreactor. We were confined in the conditions because this is a test system, it's not an operational system. We had to limit the daily provision of CO2 to this reactor to 1 G, which also influences the amount of oxygen that the algae are giving up. You see here we are limited to 7 to 9% inside the experiment container of CO2. The oxygen content should not be more than 25% for obvious reasons, fire and such. So we start venting, doing an oxygen absorption if that is reached. And also the relative humidity inside the experiment container needs to be controlled by our sensors, which you see here. Okay, next. The experiment, the result of the experiment can be assessed by doing an optical thickness analysis of the fluid that we have in mind. And because we expect a quite sizable change of the optical thickness by the algae, we have deployed 2 sensors of different intensity that go through and finally come up with the optical thickness, optical density of the fluids, where we can then judge with the right calibration scale in how far the algae thrive well and are growing. And other sensors for pH and the gases supplement our control possibilities. We have syringes that feed the initial algae into the photobioreactor, and we are also able to take samples with the help of syringes in order not to overpressure the loops. They are very sensitive, this membrane. We have devised a system that would immediately take out, at the same time take out fluid and inject fluid at the same rate, so that we are not coming into an overpressure situation. Other syringes are provided to feed media, mostly nitrate-containing media, into the algae to keep them in a good nutritional state, and also return to Houston bags, as you can see here, are provided to get the samples down in one of the download opportunities. That was our original plan. So we wanted to go 6 months of operation after the experiment start with the inoculation of the algae, then let them go, take samples from time to time. You see the gray ones here. These are the samples that we wanted to have down. We insert nutritional media. This is the blue ones to keep them happy and feed them the nitrate that they need. And it turned out that due to difficulties on board, this was the achieved result of the experiment. It was cut short by a power failure after 2 weeks. That's how it goes with experiments. That's the experience that the group has to cope with, but we made the best out of it. We have a sample here that was taken at the right spot of time. And luckily, we could persuade mission control, and the astronauts were so nice as to come up with another sample after 12 weeks. At that time, the algae were already a long time under non-optimal conditions. We know that, and we take that into account because we run a parallel experiment on the ground. So we pulled the plug at the time. At the time, we got this message from space that we couldn't recover from from this failure, and let the calibration experiment, the reference experiment, run the same way as the algae in space. So, conclusions. We have at least made the experience that we can start this experiment. We see first indications that the optical density of the algae is growing as we have foreseen. We cannot tell about the long-term effect, but at least the start of the experiment looks very promising. And we have samples returned with SpaceX 18, that we now can analyze, and we look into the morphology, we look into the growth kinetics from the data we have and from the samples that we have. We can compare that. We look at the uptake of phosphate and ammonia, which are the nutrients that we provide. We look into clipped genes, whether radiation really plays an effect and has a sizable effect on the algae. And for sure, we also look whether something has grown inside these photobioreactor loops that we didn't want, like fungi or whatever algae bacteria. And this is the immediate optical comparison of a healthy sample taken after the 2 weeks and a sample that we got back after 12 weeks that has been for a long time under non-optical conditions. And you see already the chlorophyll, the photosynthetic units deteriorate, obviously, when not held in optimal condition. So thanks to the astronauts that made this possible, thanks to all the industry and DLR folks and the group at the Institute of Space Systems in Stuttgart for pushing this experiment. It's a technology demonstration, but en route to exploration, we need to make these small steps to do the big leap in the end. Thanks you for your attention. Questions, please? Yes, please.
What does it taste like, the biomass that you're making?
Algae. You have them 5% in organic food. You have 5% or so complements of algae. Look at the description. Algae are something like you have a sushi, the outer part of a sushi. If you chew that is algae.
But did you choose your strain according to taste?
Yes. The main choice for Chlorella vulgaris was it's a robust algae that you can pump, that doesn't lose its mechanical integrity by being moved around, contrary to other algae, but it's also high on protein. So that this is a very good byproduct that we have a lot of unsatisfied, fat acids and proteins that go with algae. If you feed only on algae, it would not be a healthy healthy nutrition. You need other stuff, but algae are fine. Alex?
What's the way forward on that one? Is there a rerun or next experiment follow-up?
Yeah. Vote for it. Yes, the initial thought is we bring it down, we look what failed, we try to get it up again. We learn from the experiment that we have now, but the Mark II will not look too different. But on the long run, yes, we want to size it. We want to scale it to something where really we can prove this is a source of oxygen that is reliable, and it needs a couple of zeros to scale it, but we are optimistic.
Hopefully the CO2 partial pressure on ISS is below 1%. But I'm a bit lost. You gave us numbers 5 to 7.
Yeah.
What kind of atmosphere is that? Is that the atmosphere, or what is it then?
That is the enriched CO2 atmosphere coming out of the life support rate. So the life support rate would enrich CO2 in order to turn it into something different, and we only feed this enriched CO2 in our photobioreactor. It's not cabin atmosphere.
Okay, and how does the enrichment work?
There, I have to point to the description of the life support rack. Maybe Alex can say a word. Whether they use micro adhesive beds and
zeolite.
It's an amine in LSR.
And we have there's several ways, but if it's LSR, it's
It's an amine-based bead, yeah.
And it just concentrates when we regenerate the bed, collect it, and I guess pressurize it, probably pressurize the carbon dioxide and feed it across.
Franz?
So if this system eventually would work and would go to Mars, how big of a plantation would we have on board?
My team wants me to be careful there. So we have produced with this 6-liter model, we have produced 0.2 grams of oxygen per day in the lab. The need of a human being in terms of oxygen is something like in the order of 840 grams per day. That tells you how we have to size it. But this is a demonstrator. It's not optimized for this task, and we have to work on it, but it's the first test to do that.
How high is the CO2 on ISS right now?
I think Scott Kelly will give you an answer on that one.
Okay. Not that high.
No.
I'm not quite sure I understood the failure there. It's nothing to do with the principle or the working of the system. I mean, the way you described it, I thought it was like a power supply or something like that. Was that the failure or something else with the mechanism of how the system works?
We exploited all available data to get the failure tree down, and we did not come to a conclusion. Yes, on Mir we would have kicked it and it would have worked again probably, but it's difficult with these electronic systems. We have to bring it down and then we know. Sorry, I can't say more.
All right, thank you very much. See, now our next speaker is Laura Shaw. Some of you may know Laura. If you don't, you'll get to know her and love her after this. But Laura is a member of, she works in the ISS program in the ISS Vehicle Office, and she is the one who is doing a lot of the work with respect to testing the advanced life support systems on the International Space Station. And so there's a lot of technical integration into the space station. But you have to understand that these life support systems, not all are just built in the United States. There's an ESA rack that's on board. JAXA has a rack that's coming. There's experiments from all over the place that are coming on board. Not only have to integrate those into the space station, make sure we have power and data and all the things that it needs, vacuum sources, but you also have to make sure they play well with one another. So if you turn on all the carbon dioxide removal systems at one time, what you'd have is no carbon dioxide, and you couldn't tell if they were really working or who was doing the hard work. So with that, let me turn it over to Laura, and she'll talk to you about our exploration life support systems.
Good morning. I have to tell you, I grew up a huge space nerd. Just to be in this room with you all is a real privilege. I'm also very privileged to be able to speak on behalf of the team that's executing the work that I'm about to describe to you. Okay, so we talked a lot today about the challenges of exploration and going beyond low Earth orbit. That's particularly true in the area of life support systems. And I'm going to call it ECLSS, so I'm just going to define that for you. Now it's environmental control and life support systems. So ISS has given us a large body of experience in the area of life support systems with the regenerative systems we have. But a lot more is needed to improve to go beyond low Earth orbit. So NASA has initiated an effort to develop and demonstrate advanced technologies in an integrated fashion on the ISS. And the objective is to develop a capability portfolio of capabilities for different that we can use when we go to different destinations. So if we're going to, for example, around the moon, we don't need as much regenerative ECLSS versus obviously a transit mission to Mars. So whenever the mission is defined, we will be ready with these capabilities. That's the intent. And our approach is to take the existing systems we have and use lessons learned from our ISS experience to upgrade those. And then as well, we're going to develop new technologies, integrate them into the integrated system and test those out as well. And I'll talk about some of that today. The objective is to characterize system performance and reliability in a fully relevant environment and a fully integrated system over a long period of time. This is most applicable to interplanetary transit missions because we can test systems for the planetary surfaces for the most part here on Earth. We really need the microgravity environment of ISS to test out these transit mission type systems. And ISS is really unique to create this capability. It's essential we use ISS as the test bed for these technologies. We can really test these nowhere else at the moment but on ISS. We need to understand and characterize multi-phase flow, particularly in ecosystems in microgravity. This is a significant challenge. We have to use relevant constituents in the crew waste streams. For example, crew urine has more calcium in it than humans do on Earth, as you're shedding that calcium. That affects our water processor. We've actually seen that in ISS. So we need to feed those relevant, highly relevant waste streams to our systems. We need a closed environment in the spacecraft so we can challenge our systems and learn how to scrub all those things out. And we need to integrate everything together with actual crew members. So ISS is the spot. It's ideal for this type of demonstration. And it really is critical, this campaign we're going through to advance those systems. So this is a graphic I like to show. It's rather elementary, but it illustrates the interconnectedness of an ecosystem. And so you can see with the crew in the middle there, they are, of course, breathing in a clean atmosphere with the right levels of oxygen, right pressures, and then they're breathing out waste products that are then removed by the different systems, trace contaminants, for example, CO2, as we talked about today. And then the crew's solid and liquid waste, of course, we use the toilet to then transfer those to a urine processor, which then is processed down to potable water in a separate system that then goes to crew for drinking, for hygiene. As well, we send water to our oxygen generation system, which then creates oxygen for crew to breathe, of course, but then also waste hydrogen, which is combined with the carbon dioxide in the Sabatier reactor to create more water, which then starts that loop again. So this shows you how interconnected and how important it is to integrate these things together to test them all together and understand how that interconnectedness works. The other thing illustrated on this chart with the stars is everywhere we're going to make an upgrade or add a new system. And you can see it's almost everything. The blue stars, are new functions. For example, there's a new brine water recovery system that I'll talk about a little bit, which improves our water recovery rate significantly. The red dots are areas we've had key failures, and CO2 removal is one I'll talk about specifically. And then the yellow are areas we're upgrading based on our lessons learned, be it issues with the temperature and humidity control, the condensing heat exchangers, that sort of thing. I'll talk more about those as well. So why focus on ECLSS? Why is this so hard? Well, it seems obvious, right? We can't resupply like we do on the space station when we're on a transit mission to Mars. So we've got to bring everything with us. And that means that, of course, the more we can reduce or recover our resources, the better. And so right now on ISS, we recover about 42% of oxygen from CO2. We need to get that to closer to about 75 to make it a viable mission from a mass standpoint. We recover about 90% of our water today on ISS. We need to get that to about 98%, and we've got a system we think can do that in order to, again, make it a viable mission. So and the other thing is we've got to analyze samples in situ versus bringing them down and analyzing them on the ground. For example, total organic carbons are an indicator of proper processing of our potable water. But if we find something, we usually bring a sample down and determine what is that thing. Well, we need to figure out what it is while we're on the way to Mars or on the way back, instead of waiting for that return. So those are some examples. Okay, so a couple of areas of emphasis for our improvements, and here's where we're going to talk about cabin CO2 levels. We've gotten a lot of experience. We've got a lot of discussions. We had a lot of discussions with the ISS crew members about the cabin CO2 levels being too high. And so our intent is to design systems to lower those levels and actually design them for that. So we, instead of 3 millimeter of mercury cabin partial pressure, which is about 0.39%. I had to phone a friend, and I just got the answer. we are actually shooting for less than or equal to 2 millimeters of mercury with our new systems. And so to do this, we're developing 3 unique systems. We're developing them, we're building them, we're going to fly them all to ISS and test them there because they behave a little bit differently in space than they do on the ground. And then we're going to find the best one, we're going to pick it, and we're going to put it in the integrated test that I'll tell you about in a little bit here. The first of those is on ISS today. It's called the thermalamine scrubber. It's actually based on the Orion unit, and the Orion unit was actually originally demonstrated on the ISS. So it's kind of coming around full circle. But that unit's on board now. It flew up in April or May of 19. We operated for about 3 months, and then we had a fan failure, so I understand. These things happen. But we refurbished that fan. We know why it failed, and it's going to launch back to ISS in December, and we'll get that system back in operation. But it did perform well, and it's very close to that 2 millimeters of mercury target that we've given. The other 2 will fly to ISS in late 2020, and then actually a commercial partner will very likely fly a 4th one, probably in 21 or 22. So this is a key area that we are focusing on to improve, really for the crew's cognitive abilities and just for their general comfort on the spacecraft. New capabilities we're adding. This is another area where we're supplementing the systems for improved recovery rates. We're adding a brine processor assembly. So this takes in the brine that's generated by the urine processor, which now has a good bit of water held up in it, and we throw it overboard today and we burn it up. There's a lot of water in there that we could recover. So this will take that brine and dewater it, and this is where we go from 90% full water system recovery to 98%. In fact, initial ground testing, don't tell anyone I told you, but looks like we might get close to 99% water recovery. We'll see how we do. We'll see how we do in space. It's one thing on the ground, it may be different on ISS. So this is exciting, and this will be on ISS in late 2020 to start its demonstration. And it will be integrated directly with the urine processor, so we can, from the ground, transfer brine from the urine processor to the brine processor. And the way this works, by the way, is it uses a novel membrane bladder. We put the brine in, and then heated air runs across it, and the water evaporates, all the nasty things stay inside the bladder, and then we recover the moisture as condensate, and we throw away that nasty bag of brine, of dewatered brine. The other area we're looking at new capability is supplementing our CO2 reduction area. This is the chemical reduction of CO2 to recover oxygen from it. And so we're looking at, the current system, as I mentioned, takes hydrogen and CO2, combines those together to make water and methane. That methane is vented overboard, but there's hydrogen in that methane, which is useful. And so we're looking at systems that can crack that methane open, purify the hydrogen that's released, and then send it to the Savatier to improve the efficiency of that reaction. And that's where that 42% to 75% increase comes from. Another area of emphasis is to make our parts and our subassemblies more replaceable. One of the driving factor for all the work we're doing is to reduce the mass, the departure mass of all the things we need to take to Mars and back to ensure we have a successful mission. ECLSS is a massive amount of that current mass. So we're trying to improve, and I'll talk about reliability in a minute, that's a key area, but also there are some systems, as they're designed on ISS, we replace components of our systems as ORUs. So you've got maybe a reactor with valves and sensors and all that in a box with QDs on it. If a sensor in that box fails, you've got to replace the entire ORU, and these are heavy. So you've got to spare a lot of these ORUs. Well, we can't really do that. It's just too much mass. So we're looking at taking out these reactors, for example, making them replaceable, as well as all the little pieces inside those ORUs. A critical area we're looking at is the oxygen generator. It's currently in a blast dome in the event we have a hydrogen leak inside to protect the vehicle, but we've actually found it's not as dangerous as we thought, as we learned on ISS, so from our experience operating the system on ISS, and so we're looking at either removing it from its blast dome or putting it in a much smaller blast dome that we can then replace, and then we can replace those sensors, et cetera. So then you're sparing just the sensor separately versus having multiple of those large ORUs. As well, on our Sabatier reactor, for example, we're putting the reactor in a place where you can actually get to it and replace it as it is designed today, you have to take the whole Sabatier system out and replace the whole thing. So those are areas. This isn't so much Eclipse technology as it is repackaging and redesigning the systems, except the way they operate and the way things are laid out, affects the way it operates. So it really is more challenging than perhaps it sounds. And then improve reliability. This is a key area. And we've learned a lot on ISS, from long duration human exposure and system exposure to these atmospheres and systems. So one key area is we've noted long chain organics, from silicon-based long chain organics, siloxanes, are pervasive in the atmosphere, mostly from hygiene products, also off-gassing from conformal coating, things like that. But these siloxanes, we have found, negatively impact the life of our water processor. They also can affect the CO2 removal beds, as well as that Sabatier. It actually poisons that catalyst. We found these contaminants way down the chain in the system where we didn't expect them to be. So we've learned a lot from ISS in that respect. So we've added these siloxane filters to the ISS. They're actually just activated carbon where the HEPA filters go. They're stacked together now. And so these are on ISS today, and we've actually seen an order of magnitude reduction in those siloxanes in the condensate, so before it gets to the water processor. So we're already implementing these improvements on ISS. We're looking at improving our urine processor. For example, the distiller that we use to purify the urine to mostly potable has had some urine carryover issues, which we will fix. We're improving the drive system of the centrifuge that spins the distiller. We've seen some issues with that on our operational experience. And then the water processor as well, there's a catalytic oxidation reactor that polishes the water to potable. We're going to make it more effective at removing those siloxanes in case some do get through, because some will probably still get through, as well as we've seen some early leakage that we need to repair. So sometimes it's just a mechanical problem with the system, and that's true in that case. So we're looking at all these upgrades to improve reliability based on our experience. So from an ISS integration standpoint, Kirk mentioned, this is challenging. We've got a vehicle that, it is what it is, and we're doing all sorts of science on it. We also need to do these technology demonstrations for exploration, but we're held in by the ISS architecture. So our intent is to mimic a spacecraft life support system as best we can on ISS. We're limited because of rack architectures on ISS, the power type, the fact that we use Mill Standard 1553 command and data handling systems, crew size changes. There's lots of things that are a little bit different than exploration, but we can work around these. In fact, we have developed a new capability for an Ethernet-based command and data handling system, which is much cheaper, much faster to develop, and we're already using that system for our technology demonstration pieces of hardware. We have assessed the ability of the ISS to support this whole effort from a power, active cooling, and actual physical locations perspective, and it is capable. There's some additional, that supplemental CO2 reduction I mentioned, could be very high power and could be large, so we may have to accommodate it in a subscale, depending on what it actually ends up needing when it matures a little bit further. So the whole objective is to improve our predictions of the reliability of the system so we can really scale those spares and understand that mass before we set off on a mission. So for ease of integration, we have the system divided into two strings, they call them, an air string and a water string, and I'm going to describe those for you in a moment. They're integrated together, I'll talk about that in a minute too, but they're integrated together with the common atmosphere on ISS, so stuff coming out of the air system can affect the water system through that common atmosphere, and also the water system, the water buses that run throughout the ISS, throughout the US segment of the ISS, integrate those two strings together. And then environmental monitors that are, checking that we're doing our work correctly are installed wherever their functions dictate. So the water processor has a water monitor nearby to check it, for example. So the air string will be located in the US lab module, and it comprises the condensing heat exchanger that removes heat and humidity, the post-heat exchanger water separator that separates the water and the gas, and then we send the water to the downstream condensate processor. The trace contaminant system, the CO2 removal system, CO2 reduction to close that loop and use our resources, and oxygen generation. That's the air string. And then the water string is the toilet that Jim had talked about, the urine processor, water processor, brine processor, and then the water dispenser which will actually be very likely located in node 1, but connected via that water bus we talked about. I'm not going to go through this in detail, but you can see this is the schematic of the system we will create. And so air comes in, here we go. Air comes in, gets filtered through those siloxane filters, goes through condensing heat exchanger, and then down, well, you see it goes out to the cabin. Slipstream comes to the CO2 removal device, gets compressed, and then the water gets sent to the oxygen generator. This is harder to do than it looks. And then, maybe it does look hard. And then those contaminants, or those hydrogen and CO2 go to the Sabatier there, and there's our supplemental CO2 reduction, bringing that hydrogen back in to improve that efficiency. And I'm going to show you a picture of ISS with a rudimentary graphic. Sorry, but it's so rudimentary, but showing you where we're going to put all this stuff. So the thermal amine scrubber is on the overhead in Bay 1 right now. We're going to put the second device, CO2 removal device, here in the port side of Bay 4, and then this third one will be up here in Bay 2 in the overhead. The oxygen generator and the Sabatier will go into the port side of Bay 1. The CO2 winner of the down select I mentioned will go over here on deck 6 where the Cedra is today. Condensing heat exchanger will be over here or on the starboard side, one of the two CCAAs. And then that CO2 reduction number 2, the supplemental CO2 reduction, will go on the right side, the starboard side, where we can run hydrogen and methane across this racked bay to the other device. So that's how we'll execute the air string. The water string, you can see the 2 toilets here. They're in that double stall that Jim mentioned, UWMS and WHC, and they'll feed into a urine transfer system, which is basically an automated way to handle urine coming from 2 different toilets, and that will send that to the urine processor, which will then send its water to the WPA, the water processor, and then the brine, you can see, is added, and that humidity goes to the cabin, and then the water processor feeds the oxygen generator and the potable water dispenser. So this is how we will do the water string, and here's a picture of it. You've already seen it on Jim's charts, but there's the double toilet stall with the UWMS inside here. That urine transfer system will be installed right there. You can see it's on a rack face. We are absolutely maximizing node 3 to the fullest extent. We've squeezed as much as we can squeeze into this module. The brine processor is right here on the overhead. We had to notch out the stall to fit it, and then you can see that's how, as Jim said, there's an exercise device on this side of the toilets and an exercise device on the other side. So it's going to be a very busy module. Now, these are all integrated together. Every one is connected as it needs to be in that schematic you just saw. So, and these are some pictures. You've already seen most of this. Just the only one that's new is that urine transfer system on the upper left, and that will actually fly on NG12 here at the end of the month or beginning of November. So our schedule is to get the majority of the airstring on ISS no later than 2023. The pacer's probably the oxygen generation system upgrades. The water string we want to get to ISS, very likely we'll get it here in late 2020, so that one's coming up a little bit sooner than the other. Brine processor, for example, will be up in late 2020, as I mentioned. And then we'll add the exploration PWD, which is a simplified version of the one we have, the potable water dispenser, probably in 2021 or thereabouts. So that is all I have. Thank you.
So we talked about, you heard about that, what's going on ISS, and of course we're also working towards some new spacesuits, which also have an ecosystem. So lots of work going on in that area these days. Let's see, I started off today talking about, I mentioned that we did a spacewalk. We were doing a spacewalk last Friday about exchanging some batteries. I told you the batteries were healthy. What I didn't tell you is the person responsible from NASA in design, development, and ultimately launch of those batteries is our next speaker. So Eugene Swanbeck is a member of the ISS Vehicle Office. Eugene's done a number of things in ISS world and space world, but today he's kind of our go-to guy for big projects, big integration projects, big high dollar value projects. So the batteries that we're currently changing on orbit right now are one of those examples, and the next is about advanced solar arrays. So Eugene's here to talk to you about solar arrays.
Thank you, sir. Thank you for that introduction, Kirk. I've been working a lot of electrical projects my whole life here at the center. I think I've been typecast. But today we're going to talk a little bit about the new solar arrays that we're developing for the ISS. I don't know about you, but I can't look at this picture and not see these big, beautiful arrays on the ISS. The solar arrays have been operating continuously since the first pair was deployed in December of 2000 on STS-97. Through the years, as more and more modules were added to the space station and it continued to grow, so did the demand for power. After the fourth and final set of solar arrays were deployed in March 2009, on STS-119, the full complement of 8 arrays that you see here today were able to support the ISS through the last stretch of its construction. These arrays were originally designed for a 15-year life, and they've been providing power for dozens of crews, thousands of scientific experiments, and continuous operations of the ISS ever since. Clearly, some of these arrays are older than 15 years, and the program has decided that it's time to consider augmenting them to fully support our goal of low Earth orbit commercialization. George showed you a video in his charts earlier on today about the rollout solar array experiment that was launched to the ISS in 2017, a very successful experiment that demonstrated this new rollout technology. What this innovative concept is some, there we go, these carbon fiber booms on either side of the blanket are a slit tube carbon fiber boom that's formed around a mandrel initially. It wants to be a round boom, but it's rolled flat on a mandrel for launch. And the deployment force is this boom remembering that it was round at one point in its life, and it's becoming a tube again, and that's what provides the force to deploy the array. And once it's fully deployed, that provides the rigid structure to hold the blanket tensioned through its life. Is it two-way or one-way? The flight experiment was two-way. The array we are designing is one-way, deploy only. There is no retract capability because our array is a larger size. Our blankets are a lot bigger than what was on the experiment. And that slit is actually closed with magnetic latches that once they close, you can't undo. So it's a one-way deploy for what we're doing on the ISS.
And the experiment wasn't successful in the retract, but it was successful in identifying what hung it up, so that if you want a deployable array that could also retract, they at least needed that, right?
Yes, and that experiment helped us characterize the performance of this technology, and it allowed the small company to come up with a design that would be scaled to the level of power that we need on the ISS. So one of the first questions we had to answer was how many new arrays? And I told Mr. Shireman, that's easy, all 8, right? Then he reminded me our budget is not infinite and we needed to take a closer look. So we examined all of our core loads, our payloads that we want to power at all beta ranges, what power we transfer to our friends in the Russian segment, and also this potential commercial module we may have on the front of the ISS in the future. And going through all the loads we would have to support, we determined that 6 channels, as you see here, is the minimum amount we could upgrade to not negatively impact operations on the ISS. This new ROSA is being supplied by Boeing, our prime integrator, and they have 2 main suppliers, a small company in California, Deployable Space Systems, which is made up by a lot of the folks who designed the original arrays on the ISS, and Spectralabs, another company in California, is providing the solar cells, who also provided the cells for the original ISS arrays. So these new arrays will help NASA meet its goal of commercializing low Earth orbit, and while we continue to do all the scientific research needed at the full capability of the ISS. What do these new arrays look like? Apologize, these are concept images. We're still building the hardware. I can't show you real pictures of it yet because it doesn't exist. But the concept is that the rollout solar array here, the green array, is going to be deployed in front of the existing array. It's 20 feet wide, approximately 60 feet long. It shadows roughly 2/3 of the existing legacy solar array, and is going to be attached down here at the mass canister on the beta gimbal assembly. That allows us to take advantage of the existing sun pointing infrastructure of the ISS. The unshadowed portion of the legacy array up here is still going to remain active and provide power. It's going to be electrically combined with the new ROSA array. So both the old top section and the new ROSA will be fed into a set of Y jumpers that will go into the primary power system of the ISS. The sequential shunt unit, the next box that this power system talks to, technically won't know the difference. It's going to increase the power level of the of each array as to what it was when it was new, roughly. How does it attach to the BGA? We're also building a modification kit. This is launched as pressurized cargo. It's all EVA installed, and it provides the mounting location for the iROSA. You can see here in this mod kit only diagram, there's 6 different struts. They're assembled IVA, then they're taken out of the airlock. These struts are attached to existing pads on the BGA mass canisters, and it provides the part we call the backbone, this blue piece here. This is the main mounting surface for the new iROSA. The initial runs in the neutral buoyancy lab have indicated the crew can install 2 of these mod kits on 2 different BGAs in a single EVA, which is very promising. The launch configuration of the iROSA, since the mod kits are installed in pairs, we're launching them in pairs on the SpaceX Dragon. They're going to go inside 3 different vehicles. We're building a deployable carrier here. You can see with 2 iROSAs stacked on top of each other. Notice that they're folded in half. That's because from a previous slide I mentioned the iROSA is about 20 feet wide. So we put a hinge in the middle of it, which you can see right here, to fold it in half to be about a little over 10 feet, 124 inches at its maximum, which makes it dimensionally the largest piece of cargo that we will have ever flown inside the Dragon trunk. Each array itself is approximately 700 pounds. In this launch configuration here, it's almost 2,500 pounds. A little brief description on the mechanical overview of the iROSA. These carbon fiber booms that I had mentioned earlier, they're a 6.5-inch diameter boom formed over a mandrel. Incidentally, they're being made by a company in New Zealand who also specializes in making sailboat masts for the America's Cup sailboats. So these guys know what they're doing. There's a hinge in the middle of the array. As I mentioned before, once it's soft mounted to the backbone, a crew member will fold the other half over here and put the iROSA in its ready to deploy configuration. All of the deployment actuation mechanisms are located right here in the center within 24 inches of the center, so a single crew member can reach all the release bolts that we have built into it. And this would be a really good time to show a deployment video, but again, since we're still developing this hardware, I don't have one. I can tell you though that we have 6 of these carbon fiber booms. They've already been delivered, and they're being mounted onto the root tubes at the end of this month. We have enough solar cells to build the first 2 arrays, so that's very promising. Inside the tip, the mandrel tip up here of the array, this is the part over here that attaches to the backbone. This is the tip. Inside the tip, we have an eddy current damper that provides a consistent resistance to meter the speed of deployment, and we can dial that into whatever we want on the ground. We're targeting approximately 10 minutes for a full deploy intention. So once it's initially released, 10 minutes later, you have a 60-foot long array. A little bit about the solar cells that we're using on this new ROSA project. We're building a 20 kilowatt array that should provide a lot of additional power for the ISS using the Spectralab's next triple junction XTJ prime solar cell. It's a commercially available triple junction solar cell on the market today. It's about 30% efficient beginning of life, which is more than twice what the legacy arrays on the ISS were. That's why we can get away with such a smaller array footprint and still generate so much power. We take 48 of these solar cells and put them into what we call a solar power module. These little rectangular sections here, which are then used to build up the entire array. There's approximately 32 of those SPMs in each column. There's 6 columns in an array, 3 on the left, 3 on the right. And this picture here on the right that I'm poking at is showing you our flex harness layout. There's harnesses that go on the back side of the array that collect the power from the tip. You get a few more harnesses the farther down you go to the base of the root tube. And ultimately they end in a set of blocking diode boards that are mounted on the root tube. And this is where the power jumpers will interface the new array and the old array, and then go into the sequential shunt unit on the ISS power system, the primary power system. So we get back to one of my favorite pictures again, the one we started with. The new arrays are all identical. They're not keyed for any specific location. They can be installed at any spot the program chooses, but we do have a recommended sequence that we're going to upgrade them initially, starting with the oldest arrays first. That would be the 2B, 4B power channel here on the right-hand side. These are the oldest arrays on the ISS. They've been on orbit 6 years longer than any other array. Their degradation is expected to be the ones that have the first negative impact to our operations, so that's why we're targeting those as the first upgraded channels. After that, we would like to do the 3A, 4A power channels. These provide power for expanded payload operations. The 3A channel supports the GEM, Columbus, and a lot of external payloads. 4A supports the lab and the GEM payloads. And then the final 2 sets of arrays over there on the left side would be the 1A and 3B power channels, which provide new commercial element power, and they expand our ability to transfer power to the Russian segment. 1A supports the lab, service module, and potentially half of a commercial module. 3B supports the lab and half of a commercial element. And that's all I have today. Thank you for your time.
So any questions for Eugene?
Thank you, sir.
We can all actually come up.
Yeah, that'd be even better.
Let's do that.
Yeah, let's all sit up here and take the questions.
Yes, sir.
Question for Eugene. You're just finished. I was just curious as to why you chose that panel width versus, say, going the full width of the original solar panels and cover shorter distance on them. And, there must have been some discussion as to
yes, absolutely. It's optimized to fit in the trunk of the SpaceX Dragon at 124 inches. When it's folded in half, it is 5 inches larger than the cargo envelope already. But we are also leveraging a heritage qualification program that Deployable Space Systems did for SSL, and that was the width. So we're standing on the shoulders of giants. Yes, sir.
For all this new Eclipse stuff, how much more power will that require?
Well, in a lot of cases, we are supplementing our existing system, like we're upgrading in place, so it's for the most part the same in that case. And then these CO2 removal devices, for example, again, we'll be turning off the ISS Seadra while we're running these other systems. So there's a bit of a give and take there. Some of the supplements, like the brine processor and that CO2 reduction, will add power. The biggest one is that CO2 reduction. It could be a very high-powered item. And that's why we're a little bit concerned about integrating that into the ISS vehicle. We're also talking about, does it trade for exploration spacecrafts? If power is, if we have a massive power source, it may be fine. If we don't, then it could be a concern. But from ISS integration standpoint, at the moment we're in good shape.
How do you scrub it? Chemically?
The CO2? Yes, we use adsorbent beads. Actually, there's 2 of them use adsorbent beads. One of them uses a microfluidic technology that's very novel that we'll test out for the first time on ISS. Yes. So the adsorbent beads, for example, you have one bed that's adsorbing, removing the CO2, and a second bed that's desorbing and dumping that CO2 off, and then they swap. And so it's constantly one or the other is.
And the other question I had, on Earth, the CO2 removal and the O2 production is one process. Why aren't we trying to look at that?
As you heard, with the photobioreactor, for example, and absolutely, just physiochemically, it doesn't actually necessarily work in the same reaction to do them both at the same time.
Work biologically.
Correct. But from a physiochemical standpoint.
Bending and riveting, and I'm not seeing any new biology in here.
Yeah, that could trade when we get to planetary surfaces, the biochemical, biological systems, bioreactors that process the urine, for example.
CRISPR and everything, you can actually customize your algae to taste well.
Yeah, there's the Advanced Exploration Systems group in HEOMD is developing different bioregenerative systems. They're just infusing later. So we're taking our current physicochemical experience and advancing those because we understand them and we can take them to the next step. And there probably is a technology infusion path for those in the future. Yeah.
See, Frank, you had a...
Yeah, Eugene, maybe you said it. When do you expect to have all 6 arrays on orbit? How long do you expect them to last to support the station? And the 2 arrays that you're not covering, will they continue to be in the loop, or will you?
Yes, absolutely. Those 2, all the uncovered arrays are still going to produce power, just at a slightly degraded rate. Okay. And we decided we could live with that on those channels. Your first question about when, the first set, 2 arrays is targeted for launch in early 2021, and then 1 year after, 2 more, 1 year after, another 2.
And then how long do you?
10-year life is our spec, but like most things, it could potentially go longer than that.
Yeah.
Yes, sir.
Gene, again, excuse me. How much is the existing arrays degraded?
It depends on their age. Obviously, some have been longer on orbit than others. We're seeing, worst case scenario, maybe about a 30% degradation on the oldest channels, and then less on the more recent ones that we installed.
So integrated, probably 20% or something down from max?
20, 25, roughly.
So we're only going back, and you heard him say we're going back to the original power level. That's because all the power system below the arrays was sized for certain current levels. So while you could today put a bigger array on and
easily
generate more power, the rest of the system can't deal with it, so it wouldn't help us. Yes, sir.
Very interesting presentations, and I've been holding this comment/question to this session because I think this is a session that should be addressing it. And that is recognizing the fact that deep space exploration will require closed systems. We've got to have a system which can operate for all the aspects of support as a closed system. And it's puzzled me from the very beginning of the ISS why this was not recognized as an upfront highest priority and a module dedicated to closed systems research and development. What I heard this morning was a lot of little bits and pieces which are a long ways from what's required for that. I heard little bits and pieces which are not very well integrated in terms of thinking of closed systems operation, and that was pointed out by Millie. You know, why haven't we recognized this as an upfront need, that there's no better platform available than the ISS?
So let me take that one.
It's all you.
I blame my predecessors. seriously, actually, I can tell you we have looked at exactly that. We have the latest rendition a number of times. The latest rendition I was part of. Mike Suffredini was the program manager at the time. This is probably about, I don't know, 6 years ago, maybe, about that time. And we were looking at flying a module up that would do all the things that Laura was just talking about. So ECLIS is probably the biggest example of where this is. Let's fly up a module. We even talked about flying up a module, closing the hatch and putting, well, we put people in first, didn't close the hatch, but you have to have a bioload, right? You need microgravity, you need bioload, and frankly, you need time.
Yes.
That's probably the biggest thing that we've learned so far. We did talk about that, and the reason we didn't do it is when you start looking at frankly, programmatic realities. When you look at the budget that's available, you look at, and it's not only the budget to build a module, integrate all these things in, but different companies, different countries, frankly, are building these things. When are they going to be ready? When can you do it? And then finally, there's the safety considerations. If you're really going to put people in a module and close the hatch, well, what happens if something goes wrong? Have you left them in a place where they can't get out? All those things, we basically threw away all the rules and said, okay, now let's look at it again. We looked through all those things, and we even looked through what we call the modulette, where we would really fly a small volume that would have the equipment. We wouldn't put people in there. And in the end, it just didn't work out. This is the best solution. So I agree with you. It is not a beautiful, it doesn't address all the issues, but it's the best we could do given all the constraints. Some of those were financial, time, schedule, and so this is.
But don't you have to get there?
Oh, absolutely, absolutely. We'll get there.
You're going to have this integrated module Lauren's talking about.
In fact, what we're talking for another reason, by the way. But if you can, it doesn't have to be an integrated module. You could actually close off part of the International Space Station, which makes some of those other issues less troubling. For instance, you close the hatch, but you have an escape vehicle on that side, and you have a cache of food and a cache of other supplies. Now some of those safety concerns go away. So we're looking at those kinds of things for the future. The way the schedule is right now, all these devices are coming up at different times, and so at some point in time, probably in Laura's schedules are the initial schedules. You know, life tends to intervene almost on every schedule. So my guess is probably in the 23, 24 time frame we'll get most of this equipment up there will be operating. And then some of these other things that we're interested in doing from a human research perspective, which is why we're looking at some of these isolation studies might be ready. So we haven't given up. We know we need to get there eventually. We're doing the best we can with the limitations that we have. Yes, sir.
Kirk, I mean, first off, I want to congratulate you guys. I feel like there's finally a real sort of organized push to really work on, which I think the most important of the problems that we can perfect on the space station. But from a program management standpoint, it feels to me like we ought to, besides just doing, which is essentially, it seems like a whole lot of separate projects together, that we ought to set ourselves some sort of requirement that we want to meet by a certain date. And the date's important, right? And it says that we want to get to this performance level on life support in general by this date, and that means the following requirements: this amount of CO2 removal, this amount of closed circuit percentage, et cetera, et cetera. And we're going to meet it by this date. And then it becomes a program whose goal has a goal. And is that something that's being considered?
Yeah. Yes.
You want to take that right now?
I do.
Goal that we have to get to by a certain date.
Yeah, so the agency has established these system capability leadership teams that are agency level teams from different areas that come together for a specific, system improvement. And so there's an ECLIS one of those. And so that community has these roadmaps we've created of, first identifying what is the gap we're trying to close, and then how do we go about closing that. And what's key is these key performance indicators, which is what you just said, of what's the target, and then how do we execute and get, evolve to the target.
But there's a big difference between, teams set up to focus on certain things and a programmatic goal at the top level.
Well,
But remember, so over the last 10 years since we've been making this dedicated effort, there hasn't been the actual program. The exploration program stood up, fell down. So one of the reasons that these teams were created was because ISS being the largest budget around, they were coming to us, and in specifics, they were coming to me. And so I went to Kirk and Mike at the time and said, look, I can make these decisions on this absorbent bed or go straight biological, but it should not be me making these decisions or recommending them. So we put together these cross-agency teams. Now, when it looks at the priority for both funding and for execution on ISS, HEO has set up a category, effectively, that says exploration critical. So that is the highest priority of what gets executed on ISS, and then the funding organizations understand that they're creating something at the same priority. The way that that's defined is if it has a design-driven need date. So effectively, are you in the critical path? So for instance, Robin Gatens, who along with Laura helped lead that ECLIS side, say, look, if we're going to be Mars by this date, we need to be pencils down by this date, we need to be flying by this date. And that informs what we have to enable on ISS to get done.
There really is a programmatic
It is.
structure. Bottom line is there is a programmatic structure. It's not a program like the ISS or Orion, but it's doing, I think, what you're intending. We can talk to you a little more about it. And it's international too. So what George described was domestic, but I can tell you we're working with ESA on this. We're working with JAXA. We're working with Roscosmos.
I completely agree all these pieces are here, but I would love to see ISS, here is our goal, publicly stated, this is what we're going to do.
And because ISS is a piece of it, we might be the laboratory, but we're not the guy, we're not the ones who set the requirements. What you're hearing is the ISS people saying, here's what we're doing, but there really is this overlying structure. So Laura and Robin Gatens are in for ECLIS. There are other systems too.
I think you guys are doing a great job with what you have. I think that what would help you is to have a think tank of half biologists, half eco NASA to sit together and talk about it. In biotech, that's how they have come along. It's by mixing disciplines.
I will say we do have several research areas under the Space Technology Mission Director that are looking at using CRISPR and other tools under a Space Technology Research Institute called CUBES, which is looking at cellular biology and how do you modify that in plants. Building at a low TRL level is not going to be ready for the integrated phases that we're looking at for ISS, but try to look at the really longer level or longer terms. And the other thing, as we're sort of having these higher level structures like the SCLT, System Capability Leadership Teams, bring on and close the loop, which seems the obvious solution, but if you look at the uncertainty of how many spares do I need, and so there's a little bit of debate as how much do you need to close the loop to have a robust system versus not closing the loop and having a system that might be more robust. So we're doing those trades to see what's the minimum departure mass solution for these longer transit missions and for planetary surfaces.
But we'll take your idea, and we'll make sure Laura and Robin are working on ECLIS.
Yeah.
We'll make sure that they
A lot of help.
will get we absolutely do need a lot of help. And by the way, we didn't talk about the hardest one, in my opinion anyway, the hardest problem for ECLIS for long duration space flight missions is when you turn it on, put a bunch of dirty humans in there for a while, and then you send all the humans away and turn it off. To me, I think that's probably the hardest problem, and we have zero experience with that. I do have a little experience with that in my house, but in general, not very much space experience, and that's going to be a really critical thing.
I should have mentioned that. You're right. We have to enable dormancy.
Let's see.
Can you talk about 3D printing or additive manufacturing? And is that show any promise for deep space? And where are we on spare parts?
We are doing additive manufacturing. We have some capability on space station. We're also looking at even how do we recycle those parts that we've printed on space station. NASA's also looking at building a manufacturing facility, a rack, and probably George can speak a little bit better to it maybe, where they're looking at both you additively manufacture, but then you need to inspect the parts. You may need to do some post-processing of those parts. There's AES, Advanced Exploration System, and Space Technology Mission Directorate projects looking at improving the range of materials. The UWMS, or the toilet system, we have one of the first, at least inside the vehicle, our dual fan separators, a titanium printed volute. And just how do you do the certification of it? Because we're putting some very caustic fluids in there once they're pre-treated, and how do you do all the quality to validate that and get comfortable with it? So there's a lot of pieces of additive manufacturing happening. We see that as a key piece of moving forward for sustainability. Even how do we reuse packaging foams. We're using small business program to take foams that now I can use a recycler to make the feedstock. So if you don't have to fly the feedstock dedicated, that really helps. And then the cubes thing I mentioned, how do we use CO2 that might be present in a Mars atmosphere to biologically make some of the polymer precursors we need to additively manufacture. So there's a lot of things happening across
It's one of those areas that industry outside of the space agency is making significant advancements on their own. So there's plenty of technology that we actually have to invest in order to spur and to progress forward. So the biggest things that we concentrate on is what about in our relevant environment? Are there hurdles in microgravity that keep us from doing it, or the specific materials that we want to use or can't use to get that past? But we flew the first 3D printer in space was on ISS. It transitioned into a commercial venture. There are other commercial ventures and other commercial interests, both inside and outside ISS, that get discussed, but we're the people accepting these rather than driving them.
And clearly it's a game changer for us long term, no question. If you're going to Mars, you're never going to take all the spare parts you want, and things always break. We all know that. Part of it's also cultural, I would say. At least I could speak clearly from a NASA perspective. We design it for a factor of 3, and then we test it for a few years to make sure it all works. And you can't do that when you build it in space. But that's the bad news. The good news is if it breaks, you can just print another one. And so part of it is really a cultural shift. And we're working on that today. We have, like you heard, we have, I think, 2 different 3D printers on orbit right now. I'll call them generic. There are some other manufacturing systems on orbit for a specific purpose. But we're using those. I can tell you, every day somebody comes forward, we need this tool. The first question is, can we print it on orbit? That's what we do. So we really are trying to not only advance the technology, but I'll say force ourselves to use the technology as well. Yes, sir.
Gene, I'm Tom Jones. Given the big array size that you've got on ISS, has there been any space debris impact damage to it, and how resilient is the system to that?
Yes, our current arrays have a couple of strings that do not function as they originally once did because of impacts. And we originally looked at mapping the arrays and trying to be strategic about which strings we would replace on the old array, which strings the new ones would take the place of. But at the end of the day, it was a much simpler design to make all the arrays the same. And they are glass-covered silicon wafers. They can be damaged when they're hit by something. They can be cracked. There's, at least in our cell design, 3 different paths per cell. So if a cell even cracks in half, it still generates half of its power. It's not completely lost, but all the expected degradation from the environment that we have been flying in for the last 20 years has been factored into the design and the size of the array to produce more than 20 kilowatts after 10 years, even with some degradation.
Thanks.
Just a quick question on the operations concept for bringing the new ecosystems online. It sounds like maybe some are going to run in parallel for a while and some are just going to be totally swapped out. The question is, what do you do with the old equipment that is there? Do you keep it on board as a spare? And if you do, where do you store it?
Yeah, for redundant functions, like we're going to have 3 or 4 CO2 removal devices on board. We have crew surges. That's first aspect. We're going to have periods of time where we have maybe 11 crew on ISS, and so yes, we will at least keep the runner-up is our plan. The primary unit goes and replaces Cedra and becomes the primary, and then the backup, the runner-up, is on the side, still in an open loop fashion where it's dumping the CO2 overboard. It's not fully integrated, but it allows us to handle those surges of crew size, and then we also get runtime on it as a backup technology in case something happens to that primary unit.
Just sounds like it's going to get really crowded.
Yes, we're cramming things in, as we're using all available space. So
let's see, maybe one more question, and then we don't want to be the reason you didn't get to eat lunch. So, yes, sir.
Yeah, you talked about debris damage to the solar arrays. Has there been a study of the rate at which radiation will degrade these triple junction arrays compared to the current arrays? What's their lifetime expected to be?
Yes, and that's how we ended up with the cell we selected. for the expected fluence that we're going to see in the low Earth orbit environment. That's why there is atomic oxygen cover glass over the cells themselves. And the radiation was absolutely factored into, the radiation degradation was factored into the selection of that cell. And again, that's how we size the array for the environment and for what the ISS is expected to need in the future.
But I mean, are the triple cells, are they more sensitive, less sensitive to radiation? I'm not familiar with that.
I can't answer that, I don't know.
It is commercially available, and I believe the company that's making them is selling them to like GeoBirds and things like that. So the data probably is. We can tell you who the company is, and you can talk to them. But my suspicion is they know that data. But in our, specifically radiation, we're relatively benign as opposed to guys going out of the Van Allen belt. And so I think they might have that data. I don't know. Let's see, before we wrap up, Ronald.
Yeah, thanks, Mr. Chairman. I just want to thank the students in Karlsruhe and Stuttgart who have been following this session in live stream. They are 7 hours in advance, and you are now dismissed.
Thanks very much.
I have one comment to make up here. First, actually, when I first came up with the title of this session, I hadn't called anybody yet to see what would happen. But I did pass it out to you members, and I got one hand raised immediately to join the session, and that's why Reinhold is up here. So the next thing I did was to call Kirk and ask him if he could help me put this together. And he said, sure, call George. And that's what I did. And then, as things go, George called all these other people, and so here you have this session. So I really want to thank the Space Station program for really being the ones who put this session together. And George,
Kirk, I'd like to thank you and your whole team for a great job this morning. And I'd like to remind everyone that as far as human spaceflight goes, this is the only program we got. Everything else is still out there somewhere. So we need to take advantage of the space station and make best use of it because it hopefully will be there for a while, and it's going to be the foundation we build on for the future. So thank you all for what you're doing. Thank you for coming up this morning. We're going to break for lunch now and then reconvene in here at 1:45.